Thank you very much. So as Christoph mentioned, my for a large part of my academic career, I've been working on model order reduction. And this is kind of a first foray into optimal experimental design for inverse problems, and also a little bit Bayesian inverse problems. So I'm really would very much appreciate any feedback, especially given that we're relatively new to the topic. Okay. So let me also just thank also the organizers of the thematic program, of the workshop, and of the workshop for letting me give this talk. So this is joint work with several people. In particular, much of what I'll present is part of the doctoral thesis of Nicole Nellison, who is currently in UT Austin while waiting for her defense, which will take place next month. So she's a former student of mine. Parts of the work were also done in collaboration with Veroy-Grepl and Peng Chen from UT Austin, and also from geophysicist colleagues from RWTH Aachen, Denise Degen and Florian Wellmann. Now, certain aspects of the work are being continued, particularly by Francesco Silva, Harshit Bansal, and also Dr. Nada Cvetkovic, who should be in the audience at the moment. So if Nada, if you're there, just raise your hand. Okay. So my talk will have three main parts. In the first part, I will tackle the deterministic setting. I'll first discuss a least squares method for state estimation called PBDW. Okay, and then I will discuss some work that we did. Oh, wait, my PowerPoint is going rogue. I'll then discuss some work that we did on applying some of the key ideas from this approach to the more standard variational data assimilation, in particular 3D format. Then in both of these, I'll show how stability considerations can provide us with a guide for optimal experimental design for the choice of measurements, and furthermore, how model order reduction can be used to make this computationally feasible. Sorry, I have no idea how to make this stop from going by itself. So in the second part, I will then look at the stochastic setting and then try to connect the method that I present in the first part to more standard techniques in Bayesian optimal, it's getting really irritating, in Bayesian optimal experimental design. And when we set out to do this, right, our goal was actually to see if we can apply similar ideas to the Bayesian setting. And in the end, we also learned some key differences between how to, sorry, give me 1 second and see. Wait 1 second, please. Let me just try and fix this. Let me just stop sharing. Let me try again. Sorry about that.
Maybe you are in automatic presenter mode.
Yeah, I thought I wasn't. So let me just try and let me try this. It was working earlier. So let me try that. Okay. So when we set out to do this, our goal was to see if we can apply similar ideas to the Bayesian setting.
Right.
Oh, we haven't. Sorry. I haven't shared.
No. Now we have your desktop.
Okay, wait. Okay.
Yes.
Can you see the Zoom window here, or?
You can see both. It's okay.
So basically, I think I was saying in the end, we learned some of the key differences between how we dealt in both settings with how we choose the measurements for the rather common case when there is model error. Okay, so in the last part, I'll try to put forward some thoughts on why these two aspects should really be combined, or at least why I think they should be combined, and discuss some initial ideas towards a more general framework that simultaneously deals with both noise, which is generally dealt with usually dealt with in the Bayesian setting, and also model error. Okay. So let me start. So let's say we're given a physical system whose behavior we model via a PDE, a parameterized PDE, where X here is the state. M represents a parameter-dependent PDE model, and U here is the unknown quantity or parameter. And we assume here that the map from U to X is well-defined and continuous in U. Okay. We then assume we're given measurements of the system's true state here, where X true is the exact true state, and these L's here are continuous linear functionals representing, I think I'll call this M later, M sensors or experiments, and big L here is our observation operator. And as we all know, so our goal in the inversion is to use this data to estimate the state that is most consistent with a system behavior. Now, you may have noticed already in this first part, I'm first assuming there's no noise, okay? And the reason is I'm first going to discuss this method here. And in this paper, the authors present a method they call the parameterized background data weak method, okay? And they do this for state estimation, initially in the case where there's no noise. Now, let me try to explain what this method does. It's essentially a least squares approximation in which they try to find the state, X star, in a space Vn that minimizes the square of the misfit or the distance between the measurements D and the predictions based on our model here, okay? Now, Vn here is a linear space that has good approximation properties for this solution manifold M. Now, for those of you familiar with model order reduction, it could, for instance, be constructed as a reduced basis space. Okay, but if not, then just assume that this is a space that approximates M. And I'll illustrate this with pictures in a second. Now, I haven't said how we actually measure the misfit here. Now, in the statistics community, the standard choice is the noise covariance matrix. But in this method that they presented in this paper, they do something slightly different. So they choose the norm such that we are essentially measuring the observable part of the distance, basically, between a particular guess X and the true state X true. Now, so how do they do this? So first, given a set of linear measurement functionals, L, right, we define what we call a measurement space, Tm, as the space of observable states. That is, Tm is the space of functions in V, or the space of in which the solution lies, that can be uniquely determined. So a basis for this space can be determined, can be constructed from the Rees representations, from the Rees representers of the measurement functionals on V. Now, for some reason, the citation is missing, but we first encountered this idea in the paper in the PBDW paper. But the idea of using these Rees representers in the context of sensor selection, we found has gone back actually as far as the 1980s in a paper by Bennett. If you're interested in the citation, it's apparently not here. I can give this to you later. So given this, we now choose our norm here such that this essentially, such that Z inverse here is given by the inner product of the Rees representers. And with this choice, the misfit here is then given by, as I mentioned, the observable distance between the prediction X and the true state X true. And by observable, I mean we're essentially taking the projection onto this measurement space Tm, okay? Now I'd like to spend a couple more minutes explaining this visually because it will help me later in explaining certain things. So let's let this blue curve, this curvy line here, represent our solution manifold M, and that lies within our solution space V, okay? Now, as I said earlier, Vn, represented here by this green dotted line, is a linear space that has good approximation properties for the solution manifold n. Pictorially, this means that if I would draw the smallest cylinder of radius E, okay, centered around Vn, that encloses this solution manifold, then we assume that this E here, called the Kolmogorov n width, is small. Okay? Now, in PBDW, they essentially replace this blue curve here by this green line. Okay, so to illustrate what's actually happening, I'm now just going to keep the green line, okay, and get rid of n. Okay. So here's Vn, the green line. Now let this plane here represent our measurement space Tm. Now remember, Tm is the space, the subspace of our solution space V that contains all the functions that can be uniquely determined by the data. So the projection of x true, of the true state, onto this measurement space Tm is that unique member of V, of this plane, right? This dot, which lies on the plane that satisfies the measurements. So note, if I now draw a line through this point and orthogonal to the plane, to our measurement space, we note that for all the states lying on this line, the projection onto Tm is still this dot. What this means is that all the states on that vertical line, on this thin red line, would satisfy the measurements. Okay. So what the PBDW method then does is it finds that member of this vertical line, right, that's spaced orthogonal to the measurement space that satisfies the data, which is closest to the green line. Now, the reason I'm taking so much time to explain this is that it permits me to visually kind of illustrate the important role now of the choice of this measurement space Tm in obtaining a good approximation in this deterministic noise-free case, okay? So in particular, if we would now do a stability analysis of the least squares problem, we would see that the problem is more stable if this inf sub constant here were as large as possible, meaning as close to 1 as possible. Now, I said stability. Stability means a lot of things, right? Or people use it for lots of things. Why is it starting again, right? When I say stability, I mean basically in the sense of like the condition number of the problem. Now, why is it more stable? Because this inf sub constant essentially represents the angle between this Vn here, this green line, and the measurement space Tm, okay? So if this constant were 0, meaning if Tm and Vn were perpendicular to one another, then the problem is ill-posed. There'll be an infinite number of states which have the same distance from Vn, okay? Now, so with this concept of the stability constant and this visual idea that affects this, of how the measurement space affects the stability constant, one can develop algorithms that sequentially expand the observation operator by using that measurement functional that increases this constant the most. And these are some of the works that deal with this method, okay? Now, there were a couple of things that I found. This is just, I'm going back to the slide on PBDW. There were a couple of things that I found attractive in the method. The first was how the observability coefficient came out of this stability analysis and how it allowed one to sequentially expand the observation operator. And the second bit is what to me seemed like a very natural way of measuring the misfit, that is measuring the observable part of what is essentially the model error in a norm that's natural to the space in which basically the solution lies. Right? However, while I found the work very interesting, I also found that there were a couple of things that by design were not being addressed by the method, but which were important in the types of applications that I'm typically interested in. So in particular, first of all, we all know noise plays a role. And second, as the name suggests, the parameterized model just stays in the background, right? It gives an estimate of the state, but it doesn't give us a better estimate for the parameter, which in many applications is also very important to be able to make further predictions. Now, I knew there was a huge body of literature on inverse problems and on data assimilation. So the first thing we set out to do was to try to take these ideas basically from PBDW and try to extend it to basically a slightly modified version of a standard 3D VAR problem. Now, here's a problem formulation that perhaps looks a little bit more familiar. So again, given data, but which might now be noisy, we now again want to find the parameter and subsequently also the state that minimizes the misfit subject now to our PDE constraint here. Okay, so the parameterized model is no longer just in the background, but front and center as a constraint. Also, since this problem might be ill-posed, we introduce as a standard a regularization term that penalizes the distance from the prime. Now, two key differences with the standard formulation is that, first of all, I've added a second set of parameters, theta, okay, that I'll refer to as a hyperparameter. And second, I'm also assuming that you may have noticed here that the PDE constraint is now linear in U for all theta. So this is now the weak form of a linear PDE, okay? Now, note here that X can therefore depend non-linearly on theta, but not in U. Now, some of you might think this is a rather strong assumption, so let me just say a few more words about this. Again, as I kind of alluded to, this assumption requires not only that the PDE be linear, but also that the dependence of X on U be linear. And by itself, this basically limits the types of parameter dependence that is admissible. However, it does have important connections to the more general case where this dependence is nonlinear, right? Wait, sorry, I accidentally, is nonlinear. And the reason for this is that when the parameter to observable map is nonlinear, what is typically done in OED is that one linearizes around a certain parameter value. And ideally, this linearization point would be taken as the map point, okay? However, we don't know what this map point is. Also, this hyperparameter theta can basically represent this linearization point in an iterative method for the nonlinear case. So while we made this rather restrictive linear assumption to make the analysis later simpler, due to the introduction of the hyperparameter, it's nevertheless relevant also in the nonlinear case, okay? Now, in addition, the hyperparameter can also represent additional inputs or variabilities in the problem. And you can think of this formulation as basically representing a family of inverse problems. So I like to think of it, let's say I'm trying to estimate the temperature in the building. Theta can, for instance, be an additional input such as the temperature outside on that particular day that I would need in order to define my inverse problem, okay? Now, again, our goal is to try to see how to choose these measurements L for now any value of this theta in some domain. So we now try to extend the ideas from PBDW and try to do an analysis of the stability of this hyperparameterized inverse problem. So standard steps would be to write out the Lagrangian of the optimization problem, then write out the optimality conditions. And when the smoke clears in the end, one can show that the solution can be bounded in terms of the input information with a positive stability constant. And this stability constant here is better behaved when these two constants I show here are as large as possible. Now, what do these two constants mean? Eta is essentially a minimum eigenvalue that reflects the smallest change in the state relative to the change in the parameter that's required to achieve it, okay? So eta is in a sense related to the modeling process. Now, beta here is essentially our stability coefficient for this problem. And as before, it represents how well the data, the measurement space, TM, can detect changes in the state caused by changes caused by the model corrections, okay? So if you go back to our picture from before, this is now the angle between the space of corrections to the model versus the measurement space, okay? However, note that now our stability constant depends on this hyperparameter theta. Now, an alternative way of deriving the stability constant yields a result that is perhaps slightly more intuitive. So in this form, we can show that here, so our stability constant here now basically represents how well the data can detect changes in the state that can be caused to corrections by corrections to U. So if, sorry, I'm moving too far forward. So if beta is 0, if this constant is 0, this means that for some value of U, the observation operator, the measurement functional, is unable to detect the change in the state, right? So if this is 0, that means these two are orthogonal. And if beta is small, then the solution to the inverse problem is, the inverse problem itself is very ill conditioned. So the question now is, how can we choose the measurements such that we can ensure the stability coefficient of this that we have here is uniformly good over all hyperparameters theta? Okay, so here's a summary of an algorithm that we proposed. So what I'd like to do now is kind of go step by step of how we can greedily choose the measurements that serve to drive up this stability coefficient. Yeah. So what we propose is this, given our library of sensors, right? And also a hyperparameter training set. We start with a particular hyperparameter and a particular parameter value U. Then from this initial value, we solve the forward model and compute the state. And then we loop over all the different sensor locations in our library. And then we choose that sensor location with the highest observability for this specific state. So we essentially choose that sensor that gives the largest delta here, where this delta measures how well a measurement functional is able to detect the unobserved part of the state given here. So what this part does is it takes out first the component which can already be observed and then tries to find the least observed part, okay? So this part of the algorithm is very closely connected to the orthogonal matching pursuit algorithm, and this was analyzed by Binev and co-authors in connection with the PBDW method for state estimation. So now that we've added a single sensor, in effect expanding our observation operator, we now pick a new hyperparameter, and we do this in a greedy step by computing our observability coefficient beta for all hyperparameters in some training set, in our training set, and picking that one hyperparameter with the smallest observability coefficient beta. In other words, the one for which the problem is the least stable, right? The one which causes that angle to be bad. Lost my mouse. 1 second. So then we find the parameter U that, there's my mouse, that realizes the smallest beta. And then we first check if our stability tolerance is reached. And if it's not, then we go back and repeat the process and we iterate until we reach a certain stability, a certain tolerance, okay? However, there's one hitch. The greedy parameter selection here relies on the ability to estimate beta over the training set D-train. However, computing beta here for all theta values in the training set can be very expensive, right? Since at every step for a given value of U, the solution to the PDE has to be computed for all theta values in the training set. And so this can be very expensive. So what we did was explore whether, instead of considering the stability constant evaluated at the full model, whether it would suffice to consider an approximation using a reduced order model. And it turns out one can show that given a surrogate model, which we assume is of flow dimension n, right? One can show that if your surrogate model approximation is good enough, such that the relative error in the state approximation relative to u can be bounded from above by epsilon, then the observability coefficient computed using the reduced solution here only differs slightly from the exact observability coefficient. And this is important because it means that it suffices to focus on the reduced system, which is very cheap, hopefully very cheap, and this leads to considerable savings in computational costs. And I think there's Omar is going to talk later in the week also in the use of reduced model order reduction in the context of OED. Note, however, that as long as this is true, right, it doesn't really matter what reduced model you choose. In the numerical results later, we use the reduced basis method, but this is not necessary, and the algorithm I just showed earlier can be used with other methods as well. Okay. I'm going to skip this. This is just a literature review of things works where model order reduction comes in this context. Okay. Now, what I'd like to show now is our attempts at extending the approach to a more general Bayesian setting, or at least understanding how that would translate to the Bayesian setting. And by doing so, we can see the connection between the stability-based optimal experimental design and more standard approaches of A or D or E-optimality in OED in the Bayesian setting. And once we've done that, then I'd like to show some numerical results for a geophysics example, in collaboration with some colleagues from Aachen. So as before, we assume that our data is again given by an observation operator L acting on our state plus a noise term, and our hyperparameter theta. And now we make an assumption that's quite commonly made, that the noise is Gaussian with zero mean, variance sigma, and a given covariance matrix sigma L. Now, note that this covariance matrix naturally depends on the choice of the sensors. Right? And that we also define, I forgot to mention, a parameter to observable map G, trying to use the notation that is commonly used. And we note that G thus depends on both the choice of the measurements as well as on our hyperparameter theta, and that our PDE is now implicitly contained in this map. So standard, I think most of you know, are more familiar with these than I am actually. So in standard Bayesian inversion, we take our prior pi naught, and then we assume this to be Gaussian, and then we compute the posterior probability density through Bayes' formula, and with our assumptions on Gaussian additive noise, Gaussian prior, and also for the case spread, the parameter to observable map is linear, then the posterior is also Gaussian with mean and covariance given by, that we can write out analytically and given by standard results here. Now, although these are standard results, well-known results, there are some important points I'd just like to make in this hyperparameterized setting. First, that the noise covariance matrix naturally depends on L, on the choice of the sensors. And also, what we want to do is to be able to choose this L here, right, for such that it's uniformly informative for any theta in the region of interest, okay? So in this context, right, as I mentioned, we want L to be uniformly informative for all hyperparameters. Now, as I mentioned before, there's also a huge body of literature on OED also in this Bayesian setting. So more well-known OED techniques typically consider optimality criteria, right, based on properties of the uncertainty ellipsoid associated with the posterior covariance matrix. These criteria all try to make this ellipsoid small, since a large ellipsoid means large uncertainty in the posterior estimate, sorry. So for instance, A-optimality minimizes the mean axis of the uncertainty ellipsoid by minimizing the trace of sigma. D-optimality minimizes the volume. E-optimality minimizes the largest axis by minimizing the largest eigenvalue. Okay. Now, these are typically already rather expensive to solve, and there are efforts aimed at trying to reduce the cost, right? However, the particular setting we're looking at has an added layer of complexity than the standard setting caused by basically this dependence on the hyperparameter theta. So what we're essentially looking at, I've said a couple of times, is not just a single parameter to observable map, but a whole family of them induced by this dependence on theta. So we did not want to go the usual route, and instead tried to use as a starting point the work we did on the deterministic setting and extended it to this Bayesian setting. Now, it turns out that one can relate the two. Right? So if you take a look at these optimality criteria, one thing that you notice is that they all take a look at the eigenvalues alpha of the posterior covariance matrix, right? And what we were able to show is that each eigenvalue alpha is bounded from above by this expression here. So this constant here is just the largest eigenvalue of the prior covariance matrix, sigma naught. And the only constant that depends on the choice of measurements is, again, beta here. And this beta is essentially an observability coefficient analogous to what we had before. So it measures how well a particular observation operator can detect a solution, a state solution of our problem, of our model, okay? So what this essentially says is that we can extend the algorithm we had before to this Bayesian setting. The only difference is that before we had motivated it using stability considerations, and here we derived an analogous coefficient, an analogous result, but motivated by these eigenvalue considerations. So in fact, what we had before is really very similar, but one key thing that we noticed was different was that the choice of the covariance matrix given here. So before I comment on that, let me just show some numerical results. Here, I just wanted to point out that the algorithm I had before can also be applied here with just some minor modifications that accounts for the noise covariance matrix. And again, as before, we can also use molar order reduction to try to reduce the computational cost. I have about 6 minutes, so let me try and show some numerical results. So to test our method, this is not going to be the system. So we're going to take a small section of this. In this initial test, we looked at a small section of this Perth basin. We assumed just a simple, so it's a semi-toy problem, meaning that the domain here is taken from actual data, but we assumed now a very simple model of just steady heat conduction. We applied our framework with the aim of estimating the boundary condition at the bottom, which is important in applications such as geothermal energy, where they want to estimate the temperature so that they know where to how to harvest geothermal energy most efficiently. But the problem is that they usually have to make very crude assumptions with the boundary conditions, right? So here we wanted to see what happens if we apply our framework with the aim of estimating the boundary condition at the bottom, which is about 19 kilometers deep. To be more precise, we expressed the flux at the bottom here as a polynomial with 5 parameters, so 2 in each direction plus the constant. And in addition, we have 6 hyperparameters representing, in this semi-toy problem, the conductivities of the different layers shown in different colors. To choose our sensor locations, we assume here we have a sensor library consisting of about 2,200 drilling locations. And at any particular location, one can take a measurement at 5 possible depths. Our geophysicist colleagues provided us with a noise covariance function based on actual bottom of the hole type measurements. And the covariance function is such that we were permitted only 1 measurement per hole. Now, since this full problem is not really tractable using just the standard A, E, or D optimality, we wanted to set up some simpler numerical tests that would allow us to compare how the iterative greedy method performs versus the more standard optimality criteria. So in this simple experiment 1, what we did is we first just chose a particular hyperparameter to do the tests with. Then from the more than 2,200 drilling locations in the library, we randomly chose 25 locations. And for each location, we also randomly chose a particular depth. And then we assumed that we wanted to select 8 out of these possible sensor locations. So for each of the roughly 1 million possible sensor combinations, we computed the noise covariance matrix and also the observability coefficient beta. And then that's what we plot here. Okay, so we compare it here with the E-optimality criterion, and to compare them, we plotted the maximum eigenvalue of the covariance matrix and beta in this 2D density plot shown here. Okay, and what we can see is that there really is a correlation between the max eigenvalue and our observability coefficient, which in hindsight does make sense, right? Because the observability coefficient is most affected by the maximum eigenvalue. So the E-optimal experimental design is shown by this green X here. For comparison, a sensor combination with the largest value of beta is shown by this blue X right beside it. But in the method we proposed, we did not want to compute all the beta values or all the observability coefficient values, but instead we did it greedily. And the result of our algorithm for a fixed value of theta is this one here. Okay. Now we wanted to see how the method performs if we no longer have a fixed hyperparameter. So we chose a training set of 50,000 hyperparameter values and then ran our algorithm over this training set and obtained this asterisk here. And what we think this shows is that they're all relatively close to one another, and that this gives a good approximation for the optimal design. We made similar plots showing at the comparing it to the A-optimality criterion and the D-optimality criterion. I have 2 minutes, so I'll skip these and go directly to the second experiment, where we now let the algorithm deal with the full problem. This time, consider all 2,200 possible drilling locations, all 5 depth choices, and we wanted to choose out of all the possibilities the 10 best sensor locations out of the ridiculous number of possible combinations. Okay, so for this, we constructed a reduced basis of dimension 92 to use as a surrogate model for our PDE. The offline stage for this took about 52 minutes. Then, with a reduced basis model and the training set of about 500,000 hyperparameter values, we then used the sensor placement algorithm to iteratively choose 10 sensors, and that finished in about 10 minutes for a total computation offline plus online, of course, with some setting up of about an hour. Okay, so here we let the algorithm run, and on this plot, we show how the minimum and mean observability coefficient improved with each iteration, and the final beta observability coefficient was roughly 0.4. Okay, so in summary, we developed a framework for iterative greedy sensor placement for hyperparameterized linear or linearized PDEs, right? And we did this based on a stability analysis in the deterministic setting and an analysis of the eigenvalues of the noise covariance matrix in the Bayesian setting. And we used reduced order models to significantly reduce the computational cost. Numerical results show that the method is quite promising, and at least it's comparable in terms of which sensors it chooses to more standard OED techniques, but in this hyperparameterized setting, especially at a fraction of the cost. Okay, now just some remarks. One of the things we learned is that the standard methods for Bayesian OED, optimal experimental design, that in these standard methods, the errors are interpreted through the noise model, right? But how this noise model is chosen makes a very big difference as to which sensors get chosen. So in particular, it's easy to lose sight of the fact that the data misfit really contains 2 parts, right? So if this was the data is given by noise plus a measurement of the true state. So if we take a look at this, the misfit is really containing not just the noise, but also this model error here. So just to clarify, because there was some confusion when I discussed this with some folks from last week's workshop, when I say model error, I'm lumping together the error caused by the mathematical model of the true physics and a discretization error. So that's all lumped in here. And by choosing the covariance matrix, right, the norm in which we measure this distance to be just the noise covariance matrix, we are in effect taking into account how the noise and the measurements are correlated, but we're not, as far as I understand, not accounting really for the physics, right? What the PDE says about how the measurements are correlated. So if I take a measurement here and I assume the noise covariance matrix were diagonal, as is often done, standard OED methods might cluster sensors and choose the next sensor very close to the first one. But the physics says that if I already have a temperature measurement here, I really effectively already have information about the temperature around it. And so I should really not be choosing another sensor close to it, but should query another part of the domain farther away. So when we realized this, we started looking in the literature to see whether this had been investigated by others. We're still plowing through the literature, but we did find some works by the group of Youssef Marzouk. For some reason, it's not in this list, but Youssef Marzouk from MIT also has some work on this, and also Georg Stadler and Alan Alexandrian. In Daon, for instance, a former student of Georg Stadler, they make the observation that if you choose a non-diagonal covariance matrix, then clustering doesn't happen, right? And this other paper, they also show that one has to choose a covariance matrix that models the correlation due to the model error. However, we haven't really found anywhere how this covariance matrix that accounts for the model error should really be constructed. I realize I'm 3 minutes over time. So although we're still trying to understand how to properly account for this in the Bayesian setting, I think that the method and algorithm I showed earlier for the deterministic setting kind of provides a way for choosing the centers that takes into account the physics, really. So one can think of, for instance, first choosing sensors based on the stability of the deterministic problem, corresponding to finding the map point first, and only once some tolerance is reached can we switch to choosing experiments based on reducing, let's say, the effects of noise. I've now used up all my time, including question time. I'm very sorry about that. I went slower than I expected. So I'll stop here. Thank you very much.